I'm looking at question 11 and also 12 at this point. And then 12, let me see, this says, what is the absolute, I think it says min on negative 12, 12. And the next one says, what is the absolute max on negative 12, 12. Okay, well, as long as our function is continuous, and I'm talking about, and yep, I did it. Absolute min of f on negative 12, 12. As long as our function f is continuous, then I'm guaranteed an absolute max and min. So on that interval between negative 12 and 12. Since the first derivative function is continuous everywhere, the original function would have had to have been continuous. If I can find the slope of the tangent line everywhere, must mean that everywhere exists. So we're okay with that idea. So I'm guaranteed that absolute max and absolute min. In order to find absolute max and mins, I must find the critical numbers of my function f, and I must put them back into the original function f, as well as the endpoints, and test to see which one is the biggest and which one is the smallest. Well, how do I find critical numbers? Critical numbers are not your endpoints, by the way. Otherwise, we wouldn't say test your critical numbers and your endpoints. The critical numbers are on the open interval between, in this case, negative 12 and 12, and the endpoints are the negative 12 and 12 themselves. So the critical numbers are where your first derivative is either undefined or equal to 0. So this is my first derivative graph. This first derivative graph is not undefined anywhere. It's everywhere defined. It's a polynomial function. It's nice and sweet. So I don't have to worry about the undefined part. I do have to look and see where is my first derivative equal to 0. And that would be anywhere the graph is crossing the x-axis. So at negative 7, negative 2, and 3. These are my critical numbers. Critical number for f, critical number for f, critical number for f. I don't want you to think it's for f prime. It's a critical number for f. So now I'm going to take the negative 7, the negative 2, and the 3, as well as negative 12 and 12, and I'm going to look at what each of those x-coordinates has for a matching y value in the original function, which is already right here. So I'm pretty much done. I've got my lower endpoint, my higher endpoint, and I have my 3 critical numbers. The highest of all these values is a 10. So the absolute max on negative 12, 12 is 10. Okay? And it occurs when x is negative 7. I can write occurs at x equals negative 7. And then number 12 is asking for an absolute max of f on negative 12, 12 again. And the highest, oh, did I do that backwards? I sure did. That is my max. Okay? And it occurs when x equals negative 7. What's my lowest? What's my lowest number here? My lowest number should be that negative 49.4. Sorry about that, you guys. Negative 49.4. And that occurs when x equals 12. So then I have my absolute max and my absolute min. Okay. Let's just double check and make sure we understand what all these numbers are meaning and how it relates back to the graph. And let's do our check this way. We have all our critical numbers lined up in order with our endpoints, okay? And we are going to look and see what's happening on the function f between negative 12 and negative 7. I can tell that when x is negative 12, my function is down at negative 14.5. But then when x is negative 7, my function is at 10. So I've just increased by 24.5. And that 24.5 is described right here on the first derivative graph. Then from 10, my function f is decreasing down to a 14.5, which means I just went back to where I was, right? I just subtracted 24.5 and dropped the function f 24.5 units. And that's what this means, negative 24.5. That means the function f is decreasing by 24.5 units. putting me right back to the same thing that I started with right there. And that was why the example that we have that gave the integral between a negative 12 and a negative 2 equaling 0, it's because there is no net change. If you don't consider anything in the middle, just from negative 14.5 to negative 14.5 is a difference of 0. And then from a negative 14.5 to a negative 0.8, these numbers go up. And they're going up by, what was that, 13.7? And that was this area right here. Of the first derivative graph, it tells me how much the original function changes. This is the fundamental theorem of calculus that says the area right here represents the change in these y values on f between the same two x values on the same interval. And then from a negative 8 down to negative 49.4 means that I've dropped quite a bit. And I've dropped that area, which was that 48.6. And that's what this represents. So if you have any of these numbers wrong, you're going to know it when you do this check and compare it to the graph. Also, the graph of the first derivative. If you forgot this negative sign on the 24.5 or on the negative 48.6, it's going to happen to show up over here. It has to show up somehow. That this isn't going to jive when you compare back to f decreasing, f increasing, f decreasing. You're going to note it. You're going to find it. You're going to see it. Okay?